Okay, calculations, we can skim through this because I'm going to say there are 3 types. I'm going to call question 12 a type 1. It's very easily identified. Given all equilibrium concentrations, calculate Kc. Okay, that's a fairly obvious type 1. I'm not going to waste your intelligence. Try it, write the expression, put the numbers in, check sig figs. I have 1 sig fig in answer because your least accurate data has 1 sig fig, 1 sig fig, 1 sig fig, 2 sig figs. Final answer, 1 sig fig. And check your unit. But you've got an answer at the back to check. I'm not going to waste time doing trivial calculations because I will be doing a couple later on. But that's absolutely trivial. We'll do something similar like that. Write the expression for Kc, put the numbers in, turn the handle, out comes the answer. Check your sig figs, check your unit. Check answer and unit at the back. Okay, in the reaction, question 13 is what I'm going to call a type 2. And again, I think this is an insult to your intelligence. So definitely be able to do it. It could easily be something like this on the exam as an easy, students would, 80% of students would get this right. They might make mistakes with the unit. They might make mistakes with sig figs. Check them, check SU. But basically type 2 says given some concentrations at equilibrium. Does that symbol make sense? A concentration at equilibrium, given some concentration at equilibriums, plus the Kc, find the missing equilibrium concentration. All right, read that question in the same reaction. So you've got the equation on the previous page. They're given the Kc, note 1 sig fig. If the equilibrium concentrations of 2 of them are that and that, note the sig figs. What is the equilibrium concentration of the missing one? Can you see it's just putting numbers in a formula, turning the handle on your calculator, coming up with an answer? I won't waste time on easy questions. I want to spend more time on question 14 because that's messing around. Note they've got a volume and they've got mole. You need concentrations. All right, let's just do the first one. This is clearly a type 1 with slightly different data, slightly harder. In fact, I might almost, if I have time, get you to do this. But if there's a couple of interesting things I want to illustrate, so let's write it out. First thing, Kc, equilibrium concentration expressed as concentrations, the only type you will have to do. So you could just write K and that'll be fine on a VCAA exam. Good idea to write Kc to remind you they have to be equilibrium concentrations. Okay, are you getting used to this? It's not difficult, people. Think products. There's only one product, it's HI, raise it to the power of the coefficient. Over reactants, H2, raised to the power of the coefficient, it's 1, leave it alone. I2, just for fun, put in the EQs. I'll keep saying, do you have to put in the EQs? No, you don't. Is it a good idea? Yes, it is. But if it's going to take you a little bit of extra time and you can't be bothered, no penalty. I hope I'm making myself really clear about that. Whoops, I better just get rid of them to make sure any new questions pop up. Okay, I think we're clear. All right, so you'd better make yourself a table to avoid careless mistakes. But first of all, let's work out the unit in advance. It's molar squared on the top line on molar times molar. Ooh, look at that, people. No unit. Well, isn't that interesting? So they're not going to check this one for units because there is no unit. Let's put the numbers in. Be careful. Set up a table, I'd say, so you don't get the wrong data in the wrong place. HI is 0.070 on 2.00. So we're talking 0.035 mole per litre. The H2 Next one we've got the mole for. Concentration is 0.020, 2 sig figs on 2.00, 3 sig figs. That equals 0.010 molar to the correct number of sig figs. The concentration of I2 is 0.0050, 2 sig figs. Please keep checking sig figs. You don't have to get it right in the working out, but it helps to make sure you don't make a mistake at the end. Divided by 2.00, 3 sig figs, answer 0.0025 mole per litre. Okay, clearly all my concentrations have 2 significant figures. My answer had better have 2 significant figures. Put them in your calculator. HI, 0.035 squared. Please do not picture it. Write the expression. That's nearly always worth 1 mark. Even if you make a total mess of the calculation, you've grabbed the 1 mark that's available for writing the expression for the equilibrium constant. Always do it. Don't just put numbers in what you can imagine is the equilibrium constant. That's a way to make careless mistakes. Write the expression, get your automatic mark, now put in the values. Okay, the H2 concentration is 0.010 multiplied by the I2 concentration, 0.0025. Nice, easy chuck in my calculator. You beat me to it to make sure I don't make a careless mistake. 0.035 squared divided by 0.01 divided by 0.0025. I get 49. And that's what's on screen, and it's got 2 sig figs. That's the correct sig figs, but check SU. You've just done a calculation. Please remind yourself, every time you do a calculation, you check sig figs and you check unit. In this case, there is no unit. The answer is just 49. So nobody's going to be checking units there unless you've got a wrong unit. Okay, determine the equilibrium constant for this reaction at 250. Trick question, can't be done. It will change. As we will see in Le Chatelier's principle. New concentrations needed. Cannot do that question. Moving on. Trick question. Never seen VCAA ask that. Determine the equilibrium constant for that reaction. This is just messy. We've got the same data. Totally irrelevant, people. This is the same temperature. Go back and check. Was that at 500 degrees Celsius? Yes, it was. The K will be the same. But this is a different expression. So the K for this expression, so this is K2, is going to be HI on H2 to the power half, I2 to the power half. Getting handy with this? Okay, that is my initial one, square rooted. Have a look at it. That was HI squared on H2 I2. Square root all of that, and you get HI on H2 I2, both raised to the power half. So the value of K2 must be the square root of the value of K1. It's going to be the square root of 49. SU. Your calculator will tell you 7. I'm going to tell you 7.0. You need 2 sig figs. There is, again, no unit. Check it. It'll be molar on molar to the half, molar to the half. No unit. They all cancel out. So 7.0 is our answer to C. And to D, oh, the sneaky. Same temperature. So it's the same reaction, same temperature. I can use the same K, but the K3, they've turned it around, the rat thinks. Write out the expression, HI squared. Please practice doing that until that is a 100% skill you could not get wrong on a SAC or an exam. You'll almost certainly have to do it. Now, check how that compares to the other one. That is just the inverse of my K1. So the answer should be 1/49. I can put the numbers in if I like, and you can do that as a good practice of a type 1 calculation. You've got all the numbers. You've determined the equilibrium. They should have said that in 2.00 cubic decimeters. So you could work out the concentrations, put them in. I bet you get whatever 1/49 is. Okay, 1 divided by 49 is 0.0204, blah, blah, blah. I need 2 sig figs, 0.020. No unit. 2 sig figs, no unit. All right, question 16. I'm just going to really roughly do this. We'll do a few more of these if you do master classes. You will do some. This is definitely what I will call a type 3. There was one of these on last year's exam. I haven't seen the statistics yet. My guess would be less than 20% got the correct answer. Students don't like this. You need to be trained. How do you recognize it? Some initial amounts, at least one equilibrium amount. That's how you recognize them. Some of them in initial, at least one is an equilibrium, either amount or concentration. And you have to calculate K. And if you don't learn to set these up in a very specific pattern, only the absolute brightest of you will ever get them right. Trust me. So it's a thing called you set up an ice table. I'm going to do it slightly differently from these notes. They're going to set up a rice table. Let's explain what I mean by running through this typical calculation. Right, here's your table. You don't have to draw up a table. So I'm going to say, and you might want to put in all these things and see what they're talking about. I'm going to say, I will start mole initially. That is my I. I'm going to have a delta N, change in mole. That's my C. I'm going to have a mole at equilibrium. That's my E in the ice. And then I'm going to have a concentration at equilibrium, because working back from the answer, I know that the Kc will equal the concentration of NH3 at equilibrium, I'm going to definitely put it in now, divided by the concentration of N2 at equilibrium times the concentration of H2 at equilibrium raised to the power 3. Please tell me you're now getting the hang of writing the expression for an equilibrium constant. It says determine the equilibrium constant. It will need a unit. Let's plan the unit in advance. It'll be molar squared on molar times molar cubed. That's molar squared on molar to the 4th. That's molar to the -2 as the unit. Right, so we'll keep that in mind for when we get there. But I'm going to need equilibrium concentrations, so I'm going to put in these values. How do I get them? I read the question carefully. 5.89 mole of N2, 8.23 mole of H2 are mixed in a 5, let's check that. They presumably mean 5-litre vessel. Please pop that in. We need the unit of the volume. I'm assuming a 5 milliliter vessel would be rather small, so it must be a 5 litre vessel. Please make that correction. Please, please, please. Didn't notice that when I was looking at this. And they react according to the equation. Okay, there's effectively a full stop there. They didn't put any ammonia in, they just mixed the reactants. It will come to equilibrium. What do I know? I know the initial mole of N2, put it in, 5.89. I know the initial mole of H2, it's 8.23. I don't know the initial mole of NH3, but reading the question, it sounds like 0. If there was meant to be some initially, they would have told you. Read on. They react according to that equation. When equilibrium was reached, it's found that 0.48 mole of NH3 had been formed. Okay, so my mole of NH3 at equilibrium is 0.48. That's where the data goes. Right, read the question carefully, put the data in. There's an imaginary 0 for the initial amount of NH3. If they wanted there to be some initial NH3, doesn't make sense. After all, you start a reaction with just reactants normally. You don't have to. You could start a reactant with some products already present, but that would be pretty crazy. So it makes sense that they've just taken initial amounts of N2 and H2, they've mixed them together in that 5 litre vessel. So I'm going to pop out the side here, V equals 5.00 litres. I need that to be in the question so that I can work out the concentrations. Now I use stoichiometry. My change in mole, this is the key step, for ammonia has gone from 0 to 0.48. It's gone up plus 0.48. Pop that in my little ice table. I'm going to pause, let you do that. Check that you are setting up an ice table without actually a table, just doing it above and below the equation. Have the equation there. Save yourself, you don't have to get out a ruler and draw up a table, but you've got to have these values in the correct rows. So if you haven't already got the 5.89 as the mole initial and the 8.23 as the mole initial and the 0 as the mole initial, that is implied in the question, but you need to know it's 0. If you're not told they put some in, assume none. That's a reasonable assumption. You are told there's 0.48 at equilibrium. You can then say, right, it's gone up by 0.48. Now do the stoichiometry. If the ammonia has gone up by 0.48, well, you can't make 2 mole of ammonia without using 1 mole of N2. So 0.48, the nitrogen must have gone down by minus 0.24, half as much. The ammonia went up by 0.48. The nitrogen must have gone down by half as much because you only use up 1 mole of N2 to make 2 mole of NH3. If you were making 1 mole of NH3, you'd have used up half a mole of N2. Say that again, I paused. To make 1 mole of NH3, I would only need half a mole of N2. To make 0.48 mole of NH3, I'll need to have used up 0.24 mole. See why it's a change? It's gone down by 0.24. Now get the stoichiometry right. The H2 will have gone down by 3 times as much as the N2 went down by. You need 3 mole for every 1 mole. Or it will have gone down by 1.5 times what the NH3 went up by. Easy to go to 3 times this. It's gone down by minus 0.7, 3 times that, 2. Yell at me in questions, and there is a question I'll go back to in a second. All right, I'm just going to check the question while you get that down. Thanks, Cindy. Excellent. Okay, that covers all the questions. Had time to get all that down? Now that's the key line, that delta N line, the change in mole, and this is stoichiometry. You work out the change. You'll always have data for one change. you do the other changes by stoichiometry, and now you're ready to work out how many mole there would be at equilibrium. For the N2, you started with 5.89, you've lost 0.24, you'll be down to 5. Let me get my subtraction right. 2 from 8 is 6. Double check I've done that right. 5.65 should be right. Okay, the 8.23, I don't trust my mental arithmetic. I'm going to get 8.23 and I'm going to subtract 0.72 and I'm going to get 7.51, and I'm going to double check that I haven't done anything stupid by adding back and getting 8.23. Yep. So now I've got my mole at equilibrium. So my concentration at equilibrium is 5.65 divided by 5. 7.51 divided by 5. 0.48 divided by 5. Watch sig figs for the end, but I've kept consistent sig figs so far. Chuck them in my calculator. 5.65 divided by 5 is 1.13. Can I justify 3 sig figs? Yes, I can. 1.13, 7.51 divided by 5 is 1.502. Can I justify that? No, I'm not entitled to that third decimal place, but I won't use a rounded off error. Nobody's checking sig figs. This is only in the middle. Haven't got to the answer yet. And my final one is 0.48 divided by 5 is 0.096. And I can only justify 2 sig figs because I've got 2 sig figs on the top line, 3 sig figs on the bottom line. So my final answer, this is the data I'm putting in my expression. 2 of my bits of data, I can justify 3 sig figs. 1 of them, I can only justify 2 sig figs. Final answer, 2 sig figs. Check SU, check sig figs, check unit at the end, at the final calculation. Okay, NH3 squared, I need 0.096 squared. See why you must have the expression. N2 is 1.13. And the H2 is going to have to be cubed, 1.502. I will not use a rounded off number in a calculation. I will have to remember to cube that. So I'm actually going to do that first. Now you've probably got a cube function. I'm going to go 1.502 times 1.502 times 1.502, just because I can't be bothered working out my cube function. That's 3.3885. I'm going to put that in my memory, so I can do the division later on. 0.096 squared, 0.096 squared divided by 1.13 divided by what I've got in my memory is 2.406878. But I'm going to think sig figs. I'm going to think units. 2 sig figs. I hope like hell that's the answer at the back of the book. Question 16. No, I didn't write down in my notes. So I'll assume, in fact, I might even just check it to make sure I haven't made a stupid mistake. I can justify 2 sig figs, and I must have a unit, molar to the -2. Better just check that that agrees with the back of the book for question 16. Oh, I haven't read my calculator right. It would help if I didn't make a mistake reading my calculator. My calculator actually says times 10 to the minus 3. So that's 0.0024. Just as well I check the back of the book, isn't it? 2 sig figs. Oh, back of the book's got 3 sig figs. Do you agree with me? One of the bits of data on the top line has only got 2 sig figs. No question about that. Your final answer should have 2 sig figs. So I agree with the numerical value at the back of the book. I disagree with the sig figs. It should be 0.0024 SU. And last year's example of this was brutal. The last mark, to get the last mark, you had to have the correct number, you had to have the correct sig figs, and you had to have the correct unit to get the last mark. It was a 4-mark question. You can see why it's quite tricky, and not that many students got 4 marks. Quite a lot got 0. A couple got 1 for a little bit of correct working, but it was pretty badly done. I'll be interested to see the stats when they come out as to what percentage got that one right. Now, there's only one valid one here. There will be more in the master classes. There will be some in your textbook. Look for them. Do you see what to look for a type 3? If you should be able to do type 1 and type 2, practice them, but they should be easy. These are the ones you really want to nail if you want that A+ on the exam. It's unlikely to be on this year's exam because it was on last year's exam. It'd be pretty mean to have it twice in a row, but you wouldn't rule it out. So you will practice type 3. What's the recognition? You're given some initial amounts. You're given at least one equilibrium amount. You're definitely given the volume if it's not 1, and you have to calculate the KC. And if you don't set up an ICE table or a RICE table, you might want to transfer all that data. So that we've got here, ratio is 1 to 3 to 2, if you wanted to put that in your table. The initial mole, that is what I've called mole initial. The change in mole, that's what I've called the delta N. The equilibrium mole, that's what I call NE, and the equilibrium concentration. So you can rule it up if you like, but there's no marks for ruling up a RICE table. But if you don't set up a table, having recognised that it's type 3, look, I've seen occasionally students get them right without a nice table. I don't think anybody that I saw marking in the exam last year had anywhere close to the right answer without setting up a nice table. So there's only one valid one here. You find some more in your textbook, practice them. We'll definitely cover that again if you come to master classes.